this video, we're going to learn how to estimate the values of definite integrals by the trapezoidal rule. Previously, we have learned how to evaluate definite integrals by fundamental theorem of calculus. This is to evaluate definite integrals by finding a primitive function of the integrand. However, sometimes we cannot find a primitive function of the integrand analytically, or sometimes a primitive function is very difficult to be found. In such cases, although we cannot apply fundamental theorem of calculus to evaluate such definite integrals, we can still evaluate them by numerical integration methods. And the trapezoidal rule is one of these numerical methods. Let's take a look at this definite integral as an example. In this integral, a primitive function of the integrand cannot be found analytically. So to evaluate this numerically, we can consider the value of this definite integral as the area under the curve y equals 3 to the power minus x squared. And then we can estimate this area by dividing this into several subintervals. And then we can form several trapezoids like this. Therefore, the value of this definite integral is approximately equal to the sum of the areas of these trapezoids. As we can obtain the upper bases, the lower bases, and the heights of these trapezoids directly, we can estimate the value of the definite integral like this. Because these four values have appeared twice in this expression, we can group them and hence simplify the expression like this. As a result, this definite integral can be estimated as 0.726172 something. Now let's generalize this result and see why we have a formula like this. In general, to estimate the value of a definite integral by the trapezoidal rule, we need to divide the interval from a to b into n subintervals. And then the width of each subinterval can be denoted by delta x. Delta x is simply equal to b minus a over n, and this is the height of each trapezoid. On the other hand, if we denote a by x0 and denote b by xn, then these x coordinates are x1, x2, x3, etc. As a result, these lengths are fx1, fx2, fx3, etc. In this way, the definite integral can be estimated by the sum of the areas of the trapezoids like this. After taking out delta x over 2 and grouping fx1, fx2, fx3, etc., we can obtain this formula to estimate the value of the definite integral by the trapezoidal rule with n subintervals. Sometimes the trapezoidal rule will underestimate the definite integral, and sometimes it will overestimate the definite integral. Whether it is an overestimate or an underestimate depends on whether the curve is concave downwards or concave upwards. When the curve is concave downwards, that means the curve will be in the form of an inverted U shape. And mathematically, the second derivative of fx is negative. When the curve is concave upwards, that means the curve will be in the form of a U shape. And mathematically, the second derivative of fx is positive. Therefore, by checking the sign of the second derivative of fx, we can determine whether the trapezoidal rule will give us an overestimate or an underestimate in the interval concerned. Finally, let's take a look at this example and see how we can apply the knowledge introduced in this video. In part A, we need to use the trapezoidal rule with 5 subintervals to estimate this definite integral correct to 4 decimal places. To apply the trapezoidal rule, first of all, we need to obtain the width of each subinterval. And it is equal to b minus a over n. So we know that in this example, delta x is equal to 0.1. Now we can estimate the definite integral by this formula. We should consider that a is equal to 0 and b is equal to 0.5. And x1, x2, x3, and x4 are 0.1, 0.2, 0.3, 0.4 respectively. All these values are obtained by adding 0.1 each time. Except the first one and the last one, these expressions in the middle should be multiplied by 2 according to the formula we obtained before. And then we need to multiply the whole expression by delta x over 2. As a result, the definite integral can be estimated as 0.4809, correct to 4 decimal places. In Part B, to determine whether it is an overestimate or an underestimate, we need to differentiate the integrand twice. We can let the integrand be fx. And then after differentiating this function twice, we can see that the second derivative of fx is less than 0 for all values of x between 0 and 0.5. Therefore, we know that the curve is in the form of an inverted U shape, and we can conclude that the estimate is an underestimate. This is how we can deal with definite integrals by the trapezoidal rule.